In the following, I want to give you an introduction to heteronuclear 3- and 4-dimensional solution NMR of proteins. Most of the concepts were developed in the 1990s, and you find nowadays many variants of the original experiments in modern pulse sequence libraries and spectrometers. However, it is often not so clear to the user how these experiments really work, what are crucial parameters, and which experiments are best suited to a particular problem. So I want to show and explain to you the basic building blocks of these experiments and, very importantly, show how you can quantitatively analyze the experiments so that in the end you may see for yourself whether a certain experiment is useful for your problem and whether maybe you can modify the sequence to get a better result. So I will show you a couple of practical aspects. The first thing is that you know your system that you are working on. How do you characterize your biomacromolecule? And this will boil down to actually getting an idea in Solution NMR about the transverse relaxation times. That's the most important parameter. And then I will introduce you to the concepts, what is used in the pulse sequence. We are mostly using heteronuclear transfer between nuclei, and the most important one is inept transfer, how you calculate transfer efficiencies. And then I introduce some concept of constant time evolution, semi-constant time, show basic pulse sequences for backbone and side chain assignment, 3D and 4D NOEs. And then in the end, I show you the additions that make the things more effective. Sensitivity enhancement, TROSI, importantly, deuteration. Then in the very end, I want to give you some practical ideas, simple rules for recording spectra, what you do for dwell time, acquisition time, phasing, and so. And as an outlook, what you may be able to do with very large proteins where all this does not work. So, this idea of resonance assignment by heteronuclear NMR spectroscopy was developed by the end of the 1980s, and it's using one-bond scalar couplings in the backbone and in the side chain of proteins. What you see here is the scalar couplings of the backbone and side chain for the individual bonds. And what was developed is to walk through these coupling constants from one atom to the next, like in the HNCO. You start on the amide proton, go to the connected nitrogen, and then to the preceding carbonyl carbon. And on the way, measure all the frequencies and then go back the same way and detect the amide proton oscillations in the receiver coil. This is called out and back. Similar experiment is HNCA that we will see, amide proton to nitrogen, then to C alpha. But there is actually the one bond coupling constant between nitrogen and C alpha is 11 Hertz. The two bond coupling between the nitrogen and the preceding C alpha is 7 Hertz. And therefore, this transfer actually also happens to the preceding one. And then you go back. So you get both resonances. But then there were other experiments that I will show you also, where you're not going out and back, but you go one way. For example, in this CBCA CONH experiment, you start on the beta protons, go to the beta carbon, C alpha, and then CO, NH, and detect on the NH. And you can do this one way, but then in case of deuteration, where you don't have protons on the side chains or alpha, you could also go out and back, starting from HN to N, and then CO, C alpha, C beta. There's these old reviews, one that we wrote, and then by Michael Sattler, actually starting from the MO courses, I think, also developed by the end of the 90s. And then there's this large article by Salzmann and the Wittrich group that used all these sequences and put it into TROSI sequences. This is an important publication. But if you really want to go into detail, then there's the book by Art Palmer
where all this is explained quite well, and it's not so expensive. And as a second edition on this, actually, I just found there's a recent review also by Louis Kay, or kind of a historical perspective, the evolution of solution state NMR pulse sequences through the eyes of triple resonance spectroscopy in 2019. Now, so anyhow, let's go into the real content. And we have to think about the efficiency of the transfer by heteronuclear J-coupling. You see this inept element. Let's say this is connecting between an amide proton and a nitrogen. That's what we do very often. You have these pulses on the amide proton and on the nitrogen. So you start with a 90-degree pulse on the amide proton, X pulse. This makes proton Y magnetization, and then this starts to evolve. But this proton Y magnetization feels now it's the chemical shift evolution, and at the same time the scalar coupling to the nitrogen. Now, you could just evolve both of these things, but then you would get a mess that for every different chemical shift, you will get a different amplitude. And therefore, you have to do something about the chemical shift and refocus the chemical shift. So in the middle of this period, you put a 180-degree proton pulse to make a spin echo. So this chemical shift goes one way, but after the 180-degree pulse, it's basically flipped by 180 and then goes in the same direction, but in the end, it refocuses. Yeah? So the chemical shift is done with, but then by putting this 180 in the middle, you actually decouple also the scalar coupling to the nitrogen. And so to reintroduce this, you also need to flip the nitrogen. And that's why you put the second 180-degree pulse on the nitrogen, and then that flips basically both parts of the coupling, gives them a minus sign, and then this gives a plus sign again. So the coupling evolution just continues throughout this whole period. And here is the basic formula that we always need to keep in mind. So we have here, if you are correct about the signs, minus HY magnetization and under the J coupling. And you write this here with this arrow. Over the arrow, you write, this has a precise meaning, that's actually the physical action. It's the Hamiltonian times the time. This is energy times time is the action. And the Hamiltonian is here in the spin operators 2 pi j hz nz. And the time that it is evolving is 2 delta. So this is really a precise mathematical term. And under this action, this minus HY magnetization evolves into antiphase. One part stays where you started with a cosine of a certain angle, and the other part goes into this transfer. So the angle is actually 2 pi j times delta. So you stay with the cosine of this angle on minus HY, but you go into this term that interests us, into this antiphase term, 2hxnz, with the sine of this angle. So you wait for 90 degrees, basically, then you have all of the magnetization transferred into this term, and the cosine of 90 degrees is 0, so you are just left with this. But most of the time, you're not doing this completely. I'll just explain the reason in the bottom here. And then after this evolution, you want to make transverse nitrogen magnetization out of this. So here we have transverse proton magnetization, HX, and nitrogen Z. We want to get rid of the proton transverse magnetization, so you apply a proton 90-degree Y pulse, the right-handed coordinate system, a 90-degree Y pulse on X. The final output is in minus Z. Most of the time, the real sign is not so important, but yeah, sometimes it is. So this 90-degree proton Y pulse makes from HX minus HZ magnetization, and the 90-degree nitrogen X pulse, now X applied to Z should be minus Y. So you get two minus signs, and in the end, you have two HZ and Y. This is after these two pulses. And when you look at the remaining term, this minus HY term, that does not really interest us, that feels a 90-degree proton Y pulse, and that doesn't do anything. So you rotate around the Y-axis, so it stays. And then usually you kill this nowadays with a gradient. Transverse magnetization just gets dephased by a gradient. Okay, so this is the transfer without relaxation. But now, and this would be this sine function here of this angle. And you get a maximum when delta is quarter of 1 over j. And the maximum is when you get the total period as 1 over 2 times j. The whole period, the two deltas. So this would be the sine term. But now, during this time, you have the relaxation happening. Transverse proton magnetization is there, and it feels the T2 transverse relaxation. So it decays exponentially normally with the T2. And so you get this additional factor of this exponential decay, and you need to multiply the two things. So the real transfer looks like this squished sine function, and the maximum is actually shifting to the left. And of course, it's becoming smaller also. You can actually calculate where the maximum is by differentiating the product, and then you find that the optimal delta delay is 1 over 2 pi j times the arc tangent of pi j T2. Now, in the limit where this pi j T2 is small compared to 1, the arc tangent of x when x is small is just x. So then you can forget about the arc tangent. When this thing is small, then you see that this would be then pi j T2 divided by 2 pi j. The pi cancels, the j cancels, and the optimal delta will be just T2 half, or the total time, so delta is half of the time, the total optimal time will be just T2. This is a very important rule of thumb when you have inefficient transfer, that you just go for the T2. Yeah, so make the transfer the length of T2. But of course, this is not working very well, because if this pi j T2 gets very small, then the whole efficiency becomes smaller and smaller, and then you're losing. So what is important is to know now the relation between the J coupling and the T2. So on the next slide here, you see T2 times that we determined at that time for a 30 kilodalton protein, interferon gamma, at room temperature more or less. And these T2 times are in milliseconds. So, for example, you have an amide proton T2 of 13 milliseconds and a nitrogen T2 of 40 to 50 milliseconds. The alpha T2 of 15 to 20 milliseconds, CO 52, and so on. You see that the nitrogen T2 is 40 to 50 milliseconds. The carbon T2 is quite a bit shorter. You have any idea why this would be? Certainly the chemical shift anisotropy is a relaxation mechanism for nitrogen, not so much for carbon. is less anisotropic. The chemical shift anisotropy for the nitrogen, I should explain, is coming from the polarity of the peptide bond. Yeah, so the electron cloud in the peptide bond is less symmetric than around the aliphatic C alpha, but is only a smaller part of the whole relaxation. It's dipole-dipole coupling to nearby nuclei. Yeah, and what is the strongest dipole coupling that you can imagine? It's the proton, no? I mean, dipolar coupling is the magnetic moment of one spin times the magnetic moment of the other spin divided by r cubed. And the relaxation is the dipolar coupling squared. And now the strongest magnetic moment is the proton magnetic moment. So this is very efficient when you have a nearby proton. So we have a nearby proton on the nitrogen. We have a nearby proton one bond away on the carbon. But the nitrogen has less dipolar coupling. Why is that? So it has a less efficient relaxation, let's put it that way. The NH bond is actually shorter than the CH bond. So the NH bond is about 1 angstrom, and people discuss this 1.01 angstrom, something like this, 0.99. But the C alpha H alpha bond is about 1.09 angstrom. So it's actually longer. So it's, but I mean, it's much simpler. I mean, I told you before what it is. No, dipolar coupling is one magnetic moment times the other magnetic moment. The nitrogen magnetic moment is smaller than the carbon magnetic moment. Dipolar coupling is 1 over r to the third, but the relaxation mechanism is 1 over r to the sixth. So this is both for transverse relaxation as well as for NOE. So this is also dipolar relaxation mechanism. Relaxation is field fluctuations, bringing the system back to equilibrium. Yeah, and if we now think that for a molecule in solution, the field fluctuations would only come from the tumbling of the molecule, then you can show when you go into these red field equations and so on, that for molecules that tumble very slowly, and slowly is not a very stringent problem. Slowly means slower than the T1 minimum of the weakest nucleus, in this case nitrogen, and this would be about 1 nanosecond or so. If it's tumbling slower than this, then in the relaxation rate equations, this is 1 over T2, you find that they are always just proportional to this term J of 0. This is the spectral density at frequency 0, and this is just basically the rotational correlation time, tau c. So all relaxation rates in this limit of slow motion, when they just come from the tumbling, they are proportional just to tau c. No matter where the relaxation is coming from, whether it's CSA, dipolar coupling, also quadrupolar coupling. I mean, this is practically very useful. So if I know one of these relaxation times, the relaxation time rate is 1 over T2, yeah? So if I know one of them, I can estimate what the others should be. So for this 30 kilodalton protein, we measured 13 milliseconds for the amide proton. This is proportional to tau c. And I should say, what is the tau c? That's the rotational correlation time. And there's a rough, so this is how fast the molecule is changing its direction in solution, no? And there's a rough rule of thumb, which I think is very useful. So the rotational correlation time in nanoseconds of a biomolecule, let's say in kilodalton, at room temperature in water, the rotational correlation time is half the value of kilodalton in nanoseconds. So if I have a 30 kilodalton molecule, the rotational correlation time is 50 nanoseconds, roughly, more or less. So if I would go now to 60 kilodalton, I would double the tau c, and then I would expect that the amide proton T2 goes down to 6.5 milliseconds. And also all the other times would be scaled by this factor of 2. And so this is the theoretical estimate, but the practical thing that you could do is measure the amide proton T2 of your protein of interest, and then from that also estimate what it would be. The transfer becomes inefficient when the J coupling times the T2 is small compared to 1. And this is the reason why this whole heteronuclear method was developed, because if you look at protons, proton J couplings, for example, between amide proton and H alpha, they are dependent on a phi angle between 3 and 10 hertz, so maximally 10 hertz. And if I have a T2 of 13 milliseconds here, then J times T2 would be 0.07. So meaning this transfers certainly on this very left side of the curve that I showed you and very inefficient. On the other hand, when I look at the proton to nitrogen, 1-bond coupling 93 hertz, multiply this with the 13 milliseconds, then I get 1.1, and the transfer is certainly efficient. And what you will see later is between the nitrogen and the C alpha, the coupling is 11 hertz. And when you're, for example, sitting on C alpha, the C alpha relaxation is fast. So the transfer from C alpha to nitrogen is also quite inefficient. And that's a problem when you walk through the backbone like this. Now, you need to somehow have an idea what is the T2 of all your nuclei. And I want to show you this one very simple sequence where you can get an idea about the T2 and also use this sequence to characterize your sample in general, see whether it's decaying or so. And this sequence was developed by Vladimir Sklena and Ed Bax, and it's called a 1-1 echo sequence. And this is a 90-degree X pulse on protons. So this is only on protons in H2O water, no labeling required. And this 90-degree X pulse on the proton is followed by a delay capital T. And then there's a 90-degree minus X pulse. And then forget about this HS, this means homospoil. This was an old way of doing gradients, but we don't need this. Then there's a delay capital delta. And then there's a second pair of 90-degree pulses, basically also X, and then followed by 2 times T, and then 90-degree minus X, and then there's a second delta delay. Now, what I want to convince you of is that this sequence is basically a selective spin echo sequence that has no excitation on water. You put the carrier onto water at 4.7 ppm. And now think what this first sandwich of pulses will do. You look at the water resonance. It's in the Z direction. You apply a 90-degree X pulse. We have learned before X on Z gives you minus Y. So the water goes from Z to minus Y. And now you wait for this delay capital T. But your carrier is on water. So relative to the carrier, the water spin does not move. So you just stay on minus Y, right? And then you apply a second 90-degree minus X pulse. So minus X on minus Y is probably plus third. So just going back to that. Yeah. So on the water, nothing has happened, ideally. But now you think of a resonance that is off resonance from water, and we are interested in amide protons, so 8 ppm, 7 to 8 ppm. And you go again from Z to minus Y, but now you're offset relative to 4.7 ppm. You rotate with 3 ppm, depending on your spectrometer frequency. And now you go from minus Y to plus X. Yeah. So now you can just wait until you have reached 90 degrees, and you can calculate this roughly for the region around 8 ppm. I forgot what it is, on the order of 50 microseconds, depending on the spectrometer. So then after these 50 microseconds, I apply the minus X pulse, but I'm in the X direction, so this will not feel it. So this amide proton resonance will stay transverse. And now you wait for this delayed capital delta, and then apply this second pair sandwich of 90-degree X minus X pulses, but separated by a delay 2t. And I leave this as a homework for you, that you show that this is basically the same as a 180-degree pulse with the excitation profile that I showed you before. And this excitation profile before, I forgot to say, this looks like this. So this is sinusoidal in the offset from the water. Yeah, it is positive here and negative here, and has a maximum according to where I choose the delay. And a 180-degree pulse will do the same thing with its excitation profile. And so all what you have is a selective 90-degree pulse here with no water excitation, then this delay capital delta, and then a selective 180-degree pulse, and then again a delay capital delta. So a spin echo. Now I can use this to measure T2. And any idea how I would measure T2? Yeah, you change the delta, no? And so you can do this here. So this was this HRV protein NEF at that time. So we have two delays, one at 100 microseconds, another one at 2.9 milliseconds. You just record maybe nowadays 16 scans or so on a normal protein. You get this black spectrum for the short delay and the red spectrum for the longer delay. And on the Bruker system, you can easily scale it onto each other, and you get a factor between the two. And then from the logarithm of this factor between these two intensities and the knowledge of the deltas that you have used, you can calculate the T2. So in this case, it was 13 milliseconds. There's one other thing that is nice about this sequence is that when you think about amide protons, they might have scalar coupling to alpha protons. And so the scalar coupling to the alpha might also evolve in a spin echo. But in this case, it does not, because the alphas are not really excited here. So it's basically self-decoupling the alpha. So it's a good measure of the T2. So then you get this idea of the T2, get an idea whether certain experiments would work for you from what I explained to you about the inert transfer efficiencies. You see here one example again. This was calcineurin, a calcium binding protein. And here you see this amide proton spectrum. We measured 8 milliseconds as a T2. The lines are pretty broad. And I forgot exactly what the molecular weight was, but it was unexpected for us that it would be so broad. But then we've actually found out that this was aggregating. And in this case, it helped just to add a detergent. And then the T2s became 17 milliseconds. And you see that the lines are getting much sharper. When you have measured these T2s, you can say that roughly without deuteration, you can do most of the experiments for a T2 with more than 12 milliseconds. But if you go to a higher molecular weight, shorter T2s, then you certainly need deuterations. And this is nowadays all known. So tertiary structures have been determined for 60 to 80 kilodalton proteins. You can do trosis with much larger molecular weights. One thing to finish this is data that we never published. We try to get very fast rotation on ubiquitin, long T2s, and what can you do? You increase the temperature. Now, ubiquitin has a melting temperature of over 100 degrees. So it's the red curve here. It's measured by CD. We did the same thing for protein G, has a melting temperature of 73 degrees. And we followed 1 over T2 as a function of temperature. And what you see here is that for ubiquitin, of course, first the relaxation rate goes down, the tumbling gets faster, but around 50 degrees, you have a minimum, and then the relaxation rate goes up again. So 50 degrees below the melting temperature. And for protein Gs, you kind of see the same thing. This is happening around 30 degrees, well below the melting temperature. And what is happening is actually these proteins undergo breathing motions well before the overall unfolding. And this messes up your T2s. Now, in this case, it's not the rotational tumbling, but it's the chemical exchange broadening that does this. And you see it not only on the amide protein, but there you can do this very, very quickly. But we also measured exchange broadening on carbonyl. It follows the same trend. So when you wonder why does your protein look so bad, it may just be because it's already in this kind of regime. I mean, interestingly, for ubiquitin, we try to get very high concentrations. And what you then see is that at about 60 degrees at high concentrations, 6 millimolar or so, it starts to precipitate. It does not precipitate if you use 1 millimolar at 60 degrees. But if the concentration is high enough, the protein is expanding and coming back together. But if there's a neighbor nearby, it just comes together and comes out of solution.